Okay, here is the mark scheme for the AS mock paper, and this is PH1, and pretty much it is the same as the summer 14 paper, give or take a few questions. Okay, I'm going to go through this cold so I can see what sort of mistakes I would make and which areas would easily catch you out. So let's take a look at question 1. Positive K on, K plus has a strangeness of +1, so what's the quark structure? Okay, so +1, so what does that mean? Well, strangeness, if you remember, a strange quark is given a strangeness of -1, which has a charge of -1/3. So therefore, if we have +1, we know that there's an anti-strange quark going on. Anti-strange will have +1/3. So therefore, we're looking for an up quark to complement it, which means that we have a charge of +1/3, the anti-strange +2/3, giving us +1, the +1, hence that's correct. What's the baryon number? Well, baryon numbers, if you remember, each quark is given 1/3, so we have 1/3 from the up quark, but the anti-up has -1/3, giving us 0 as a baryon number. In other words, it is a meson. What's the antiparticle of the K+? Well, if the K+ is an S bar U, then the antiparticle will be an SU bar, which in effect is the K-. These are all 1 markers, so straightforward. Nothing there that you couldn't recall from just reading the textbook. Okay, now we have this decay, so our meson turns to a lepton and another lepton, an anti-lepton, in actual fact. That the muon, is a heavy electron, so this is an antiparticle there. So, classification, is it a charged particle? The K+? Yes, of course it is. Is it a hadron? No, we've talked about that before up here. Is it a meson? Yes, baryon number of 0. Is it a charged particle? Yes. No, that is a neutrino, it's not charged at all. Is it a hadron? No. Is it a meson? No. What about the anti-muon? Is it a charged particle? Yes. Hadron? No. Meson? No. So once again, I'm hoping you would have got that just from recalling basic material. Okay, what's conserved and what's not conserved? Okay, so any of those above ideas we can talk about as being conserved, which would be baryon number, even lepton number, or even, yeah, so baryon number or lepton number. What's not conserved? Well, I mean, this is a gift of a question. Strangeness is not conserved with the weak force. And also in this instance as well, kinetic energy would have been a reasonable answer. Kinetic energy doesn't have to be conserved in, in interactions. Okay, let's go through this bit then. Here's another possible decay. What could it be? Well, first of all, let me just write this decay out. We're familiar with conserving baryon number, lepton number, and charge. So let's just work those out to start with. Our baryon number for this is 0. We worked that out before. This as well is a meson. So that means that we have 0 baryon number there. So therefore, this must be 0. So we can say it's either a meson or a lepton. What about lepton numbers? It isn't a lepton. This isn't a lepton. So we can't suddenly pop out one lepton on its own. So I think we can say that's not a lepton. Let's take out the lepton. What about charge? +1? +1? That must mean we have 0 charge. So we have a meson with 0 charge. Therefore, is that right? Let me just double check. Meson with, yes. So, is it an electron? No, that's charged. Is it a muon? No, because muons are leptons. Is it a negative pion? It's not charged. Is it a neutrino? No, that's a lepton. So we're taking out leptons. There and there. We're taking out anything charged as well, which leaves us with these two here, but the baryon number must be 0. You know the neutron has a baryon number of 1, therefore it's a neutral pion. Give a reason, one reason, well, we could have conserved, we could say baryon number needs conserving. and this must be a meson, and explained above, or you could do the same for the lepton number, or indeed you could do the same for charge if you want. So you only need one of these three to explain that away. Okay, so I hope that's a first. I mean, they always break you into these things nice and easily. That was quite a straightforward question just from recall. Okay, the second one, we're given neutrons and nucleon numbers, and I hope you can remember that the nucleon number is both proton plus neutrons. So the difference between these two, if this is neutrons, will be the number of protons. In other words, we have 6 there, we have 5 there, we have 6 there, and we have 8 there. So which one contains the fewest protons? Q. If you remember which two are the isotopes of the same element, element dictates the number of protons. Anything with the same number of protons is the same element, hence we have P and R. Explain which one has the smallest specific charge. Actually, only 2 marks. I mean, that's quite, they could be a lot harsher with that and offer 3 or 4. But let's remind ourselves of what specific charge is. So, specific charge is equal to the charge divided by the mass. Or in other words, the charge, which is the number of protons multiplied by E, divided by the number of nucleons multiplied by the mass of a nucleon. So let's just take a look at them each in turn. Let's look at P. P is going to be a ratio of protons 6 over 11. Q is going to be 5 over 11, R is going to be 6 over 14, and S is going to be 8 over 17. So this is the one with the smallest specific charge. So you get 1 mark for identifying R, and 1 for that fraction, which is the same as that ratio, which is the same as, once you multiply it by 6 by 1.6 times 10 to the minus 19 over 14 lots of 675 times 10 to the minus 27 gives us something like 4.13 times 10 to the 7 coulombs per kilogram. So you needed that bit, or even that bit to gain the second mark. This first one would be R. Okay, what's next? So we're asked for a beta decay. And in a beta decay, well, this is beta definitely, and we should just know that. It's an electron. It has no mass, but it has -1 charge. In a beta decay as well, we are left with something with 1 more proton, but no change in nucleon number. This is actually nitrogen. And also in that change of a proton, neutron going to a proton plus an electron, the beta, you also get the production of a neutrino. And when we conserve lepton number, that is a lepton, so this must be an anti-electron in order for that to work. So 1 mark for this, 1 for that, 1 for that. Super, no surprises so far, but what about the strong nuclear force is responsible for keeping the describe how it varies. Okay, 3 marks, 3 points here. We can say that at distances less than 0.5 femtometers there is repulsion. At distances between something like 1 and 3 femtometers, this is taken straight from the textbook, we have attraction. And then finally, at distances which are greater than 3 femtometers, the force is 0. Now that's important to say, it's actually 0. Saying something like negligible will not get you the mark. You need to say it's 0. Or indeed, you could say it's short range, which implies the same thing. So 1, 2, 3. Nothing for saying it's negligible. Right, what's the type of interaction between protons in the nucleus? Well, you know that protons are working on electrostatic repulsion, which indeed is an electromagnetic force. What's the exchange particle? What do you think about electromagnetism? Hopefully you should know that those are photons that carry the electromagnetic force. Write it out thoroughly, don't be too lazy. That did get a mark in this instance, but might not have otherwise. Okay, so fairly straightforward, a little bit of textbook reading for some of those, but actually straightforward. Right, the next one, a bit of wave-particle duality here. What property can you have? Okay, so diffraction's the obvious one. You see electrons coming in through graphite, and you start to see a diffraction effect, which produces rings. Of course, the diffraction effect comes from interference. Or even superposition. So any of those got your mark. What's the wavelength of the electrons? Okay, right. We are calling upon our knowledge of the de Broglie equation, de Broglie if you prefer. The wavelength is Planck's constant over the momentum, which is the same as Planck's constant divided by mass times the velocity. A simple case of plugging in the numbers. It does get a little bit more complicated because there are 3 marks here. Let's just plug in the numbers. We are talking about electrons travelling at a speed of 9.11 times 10 to the minus 31, 2.5 times 10 to the 5, and that gives us 2.91 times 10 to the minus 9 meters. The third mark has, so 1, 2. The third mark here is realizing the number of significant figures given. Because of course in the data sheet these are both given to 3 significant figures. This is only given to 2, so the answer should only be 2 significant figures, and that's where the third mark comes about. You should do this in all questions, however they're only going to really pick out one of the questions to make sure that you've attempted this. 3B was the one in this paper. Okay, what about the speed of the muons? Well, a little bit of rearrangement of that equation should give us V is h over m lambda. And you can plug in the equations. However, there's a much simpler way of doing it, and that's realizing that actually you've got h over, and then you have 207 times the mass of the electron by the wavelength, which really means it's the same thing as the previous velocity divided by 207. I mean, you could, if you want, just go through and expand all that out and work it through using previous wavelengths. However, there's a bit of a quicker method that way, and that will give you something like 1200 meters per second. Good. Okay, now photoelectric effect. Explain why electrons have a range of kinetic energies up to a maximum value when you have a light incident on a surface. The electron's kicked off with a certain amount of kinetic energy. It comes in with a certain amount, the photon comes in with a certain amount of energy, and the surface itself has a certain amount of energy that holds the electron to the surface. So that's what we're trying to describe in 3 marks. So therefore, what we need to do is the following. We need to say the energy of the photon is, I suppose, how do we describe it? The energy of the photon is fixed. So therefore, and you know it's a 1-to-1 interaction, so the energy to the electron given to is fixed. You know that the third point, the electrons need to overcome the work function in order to be kicked off. So therefore, the kinetic energy is equal to the energy of the photon minus the work function. So you'd imagine if you left it like that, they would have a specific kinetic energy. However, why is there the range? Some electrons are deeper in the metal. So they require some energy to get to the surface and then be released. The surface electrons, therefore, will have the maximum value. So you get a commentary for there being fixed values, you get a commentary for being over the work function, and you get a commentary that some are deeper in the metal. Show the work function is. Okay, so where do we have? We are given a frequency of light and we're given the kinetic energy. So we can say to ourselves the energy of the photon minus the kinetic energy gives us the work function. Same thing, HF minus the kinetic energy. Let's plug those numbers in. 6.63 times 10 to the minus 34. The frequency of light is 3 times 10 to the 15. And minus from that the given value of the kinetic energy, which gives me a final value of 2.89 times 10 to the minus 19 joules. And in order to convert joules into electron volts, I merely divide by the charge on the electron, on the number of electron volts in 1 joule. So you divide this by 1.6, gives me 1.8 electron volts, QED. Okay, what's the threshold frequency? In other words, what's the work function that's stated as threshold frequency? Well, simply that is the work function divided by Planck's constant should give us the threshold frequency. Taken in joules this time, so I take this value here, divided by 6.63, 10 to the minus 34, Planck's constant, gives me 4.4 times 10 to the 14 hertz. Good. Okay, carries on now. A descriptive point. Explain what effect the emitted electrons of decreasing the frequency. So, a decreasing frequency, but the intensity is constant. We're looking at the emitted electrons. Okay, so we are looking at, in this area here, the energy, which is the same as the intensity, is constant. The light pouring in has decreased, so E equals HF. The energy, of course, which is the energy of a photon multiplied by the number of photons. Okay, so if the energy of the photon has, so the photon frequency's gone down, that must mean the whole of this factor has gone down. And if I multiply that by the same number of photons, I will get a reduced intensity. But I want that to be constant, so in order to make it back to where it was, the number of photons need to increase. So in short, each photon carries less energy because E equals HF. F has been reduced. So to keep intensity constant, the number of photons has to increase. Mark, mark. That is tricky. And that's one that would definitely have caught me out. Right, next one. State and explain the effect on emitting electrons of doubling the intensity whilst keeping frequency constant. Okay, so now we have, in this instance, we have twice, so you've got twice the intensity of radiation. The frequency is constant, so therefore you have an electron will be given off from one of them, and the other one electron will be given off. So if you double the intensity, you double the number of electrons, but they have the same kinetic energy given they break free of the material. So that makes sense. If they don't, if they have more, or in other words, the energy is greater than the work function. Okay, I think that's really important there, just to focus on those answers. That is a really critical point there. You're only if it's greater than the work function do you get double the number of electrons, but each electron holds the same kinetic energy. Put in quite a lot there. I'm just going to check the mark scheme to see how much it was requiring, because only for 2 marks, but you can explain a lot. They asked for the use of an increase in the electrons, and the doubling, because the number of photons double. So photons double, that's important. So that's something I missed out there. Photons double with doubling the intensity, therefore the number of electrons double, and they're not too worried about that part. Well, fair enough. Okay, let's look at question 5. Next bit coming in. I'm going to try and, we need to, I might even redraw this on the other page. However, simply what we've got is we have, of course, a standard internal resistance setup. You've changed the value of the resistor, the external resistor, the load resistor, and therefore the power has changed. Okay. So to describe how the power dissipation Y varies as it increases. So what you're trying to do is, you're trying to describe this graph. It's 2 marks, and what you're looking to get is, you're looking to describe the shape with not much extra theory than just merely saying you have an increase in power up to R equaling about, what's that, 3 ohms, then a decrease in power. You're not looking to really understand anything, a comment on the maximum power theory, though this is what it's alluding to here. You are just looking to get that, for those 2 points, to get your 2 marks. You could alternatively have said 3 watts here, so you could make reference to the other side rather than this side. But either of those would have got you the full mark, so up to a maximum. But you needed to state this one. So if you're ever given a question with the graphs, make sure you state exactly the values, don't just describe loosely. Okay, calculate the current through the battery when it's running at. Good, so you're given power, and you know the power and the current and the resistance. So you need to make use of that equation. You're asked at 0.8. So 6 volts. Good. So which values are we going to use then? We're going to say that, yep, you're looking for the current. So you're looking at the current in the battery, you've got the power, and so on. So we have, let's look for the 0.8 value from here. 0.8, 1, 2, 3, 4, 5, so it's the 4th value up. That, I would say, is a pretty spot on, 1.9 watts. So I is going to be P over R, so I've moved that down to there and I'm square rooting it. 1.9 watts found from above, divided by 0.8 ohms given, square root it, and that should give me 1.54 amps. Of course, I've only got two significant figures in each, so 1.5 amps is my final answer. Okay, what's the voltage across Y? So now we have worked out the current flowing through the circuit from the battery and the internal resistance at 1.54 amps. What's the voltage? Or the PD, the external PD? Well, it's simply I times R, which gives me 1.54 times 0.8 giving me 1.2 volts. Straightforward. Straightforward. It might be worth mentioning here that you need to be very accurate. The extra mark given here is the range which this falls in, because the way they see how closely you've measured this is by looking at how close your answer is. So the third mark is whether you're in the range, and the other marks are whether you're processing marks. What's the internal resistance of the battery? Well, let's go to our full-on equation, find the data sheet, and we're looking for the internal resistance. That's E minus V divided by the current, which is R. The E is 6 volts minus 1.2 at a current of 1.5, giving us about, let's plug that into the calculator quickly. I think it's going to be 6 minus 1.2 divided by 1.5, 3.2 ohms. Good, a mark for using the equation, a mark for getting the answer. So that answer needs to be in a certain range again. So look at how accurate you can be. Student repeats the experiment. Ah, here we go. But negligible internal resistance. Now that is negligible there. Let's imagine that doesn't exist. That is a short circuit through there. Then what does that mean? Well, if that's a short circuit, suddenly E minus V is IR. The internal resistance, so that goes to 0, so the EMF is equal to the voltage. In other words, this will constantly be the EMF across there. That doesn't change. Of course, as you change the resistance, the current changes according to EMF over R. So what will the power be? Well, the power here is going to be the voltage multiplied by the current, which gives us EMF over resistance multiplied by the EMF, which is EMF squared over the resistance. So in other words, P is proportional to 1 over R. Therefore, how's it going to change between 0.5 and, I've done most of the explanation up there, but you say that the power, so you go, I would suggest it's inversely proportional. So, yeah, so power would decrease as R increases. You say that the voltage is now equal to the EMF. So the power is proportional equals E squared over R, which is proportional to 1 over R. 1, 2, 3. Good. I hope that's made sense. In actual fact, it will look something like that all the way down. Good, question 5 done. Okay, let's look at 6. Define resistivity. Okay, now this is really quite hard because you know that, let's start from resistance is resistivity L over A. So therefore, resistivity is going to be RL over L. Good, but That's, I mean, you could define it in a huge number of ways, quite verbose ways as well. But be precise. That's the equation you're looking for. So therefore, you state that equation, and you define the values. So 1 mark's coming from that. Define the values. So A is the cross-sectional area. That's important. If it's not cross-sectional, if you just give area, it's not right. Cross-sectional area is 1 mark, or at least one of the definitions given, and L is the length. So you need both of those for 1 mark and the equation for another mark. Okay, what's significant about the critical temperature? I always teach this as you need to say that as temperature decreases, the resistance decreases. Then as you hit the critical temperature, the resistance drops to 0. That's how I remember it. There's only 2 marks here, but you could get 3 there. That's how I remember it. Here it's asking you to state the significance of it. So you say below critical, the resistance becomes 0. If you write resistance is low, that does not get a mark. It hits 0. It doesn't just slowly, or it doesn't get very, it actually hits 0, and that's very important. Okay, you get 4 marks. You're asking for resistivity, so instantly you should be able to put ohm meter in there. That's your 1 mark straight away. And then, let's look at it. So, resistivity is R L over A. No, A over L. Reading that the wrong way around. I'll write it again. Which gives us 0.7 by a length of 4.8 by a diameter of, so you're looking for an area, cross-sectional area, pi, radius. Well, first of all, change the millimeters into meters, divide it by 2, and make sure you square it. And once you've plugged all that into your calculators, you should come out with something like, my brain's not working quick enough to do that, and then we should get an answer of, that's right, about 1.15 times 10 to the minus 7 ohm meters. 1.2 times 10 to the minus 7. Look at the significant figures. 2, 2, 2, because it's got the 0 on it, so it's 2 still, so 2 significant figures. Let me take one more look at that. And make sure that's the right value. Oh goodness, what have I done? Sorry, I've put those the wrong way up. It's resistivity is RA over L. So it's 0.7 by pi 1 times 10 to the minus 3 over 2 squared divided by 4.8, giving us. So that is the correct value, sorry. Ignore that bit. Ignore that bit. So just the wrong way up. Apologies there. So once you follow that through, there are 2 significant figures. Boom. Use of, remembered to halve, answer, unit, 4 marks. Well, that's a bit of a mess, so that couldn't be better. Okay, question 7. The ones they love to hate, it's the big 6 marker. Now, the way that they mark this, well, first of all, the way I suggest you tackle it is you tackle it as thoroughly as possible, showing all your finesse that you can. The way that they marked it was very interesting. They were just looking for 4 major points, of which they were seeing how many of these 4 points you gathered in your answer. I'll show you that at the end. How I would have done it is this. Details of measurements, temperature, how temperature varies, YR, and then how to use it in real life, in a room. Okay, let's take the measurements first. So you are looking to design to plot the graph of a thermistor, show how the reading on a voltmeter, so the voltmeter changes with temperature. Okay, so you're looking at how this changes with temperature. So, let's go old school here. What's your independent variable? What are you changing? Well, you're changing the temperature. What's your dependent variable? Well, you're looking at the voltmeter. Okay, so that's what I mentioned first of all. Then I would suggest that you have, how are you going to change the temperature? Well, the temperature, you want a range. So you're looking to how do you get low temperature and how do you get it hot? Ice, kettle. Okay, third part. Why is the need for R? Well, if R was not there, all of the voltage would be across there, so this would permanently be fixed. So you've got a potential divider. Some commentary to that effect. And how do you use a room? Well, once you've got all these readings of T and V, what do? Well, you plot what's known as a calibration curve. Okay, so you need to put those in order. I mean, I've stated those all in order. Shall I tell you what the mark scheme is actually looking for? They have, break them down into 1 and 2, 3 and 4, 5 and 6. So, and in order to get the 3 and the 4, in order to get these, let me just write down what they were looking for. They were looking for record voltage for varying temperatures. That's the first thing they were looking for. Then they wanted you to use a water bath which included ice and a Bunsen burner. Then they suggested R for a potential divider, and finally the graph. Now in order to hit 1 and 2, you needed, oh, and also they talked about, I'll put this on, stirring the solution. They also talked about calibration. And yes, so let's go back. So that's really, these are the major points, and this is finesse. In order to get 6, you needed to include one of these finesses. In order to get 5 or 6, you needed to have 3 out of 4. Let's just check. So you needed to include this one. Let me actually put this down as A, B, C, D, E. You needed to include D and 3 others. In order to be 3, 4, you needed 2 others and 1 other. That's right. So, let's go through that again. In order to get this, you just needed 1 of these. In order to get 3 or 4, and I decide between the 2 based on how well written. So how well written, I decide on those 2. You need 1 of those. To get 3 or 4 marks, depending on how well written, you need 2 of any of those. To get 5 marks, you needed 3 of any of those. To get 6, you needed 4 of them, and you needed one of these finesse object ones there. and it needed to be written well. But in all of these, I suggest start as you learnt in Year 9 and below. What are you varying? How are you going to vary it? What are you going to do? Why is there any extra part in the thing? What are you going to do with your results? Okay, finally it says then, design experiment is repeated with a voltmeter connected across R instead. Explain what happens. Well, if it's connected, well, let me redraw that. I'm going to redraw to being. If we connect it, 3 marks here, voltmeter across there. Now, as the temperature increases, the resistance here will decrease, thereby meaning the voltage will decrease because V equals I times R. And because this is shared between the two, as the voltage decreases here, the voltage increases over that one. So very simply, as the temperature now increases, the voltage increases, and as the temperature decreases, the voltmeter decreases. In other words, it's opposite. You needed to say, talk about the share of potential about the two resistors. That got you a mark. And therefore, as the temperature goes up, the resistance goes down, so the potential around the thermistor goes down, hence the potential around the resistor increases. Okay, I hope that all makes sense.